All right, welcome to a brand new series I'm going to be doing over the next few weeks. It's going to be called Real World Networking. So we're going to focus on network engineering as it would be relevant and as you would see it in the real world. So if anyone has been watching this channel, I had originally started it with the intent to motivate myself to go for the JNCIE SP exam. I went all the way through that process, took the exam and failed, but the channel was never intended to be purely about me going and taking that exam. It was meant to be a channel about network engineering and more broadly just computer literacy in general. So yeah, this is going to be a shorter series. It'll just be at most a few weeks long. I'm still thinking about the retake of my JNCIE SP. I've got until the end of August for that, but for now I will be focusing on this. So the first thing I'm going to do is read a blog post called "What Really Happens When You Navigate to a URL." Oops, I gotta hit Control and click for that to come up. Aha! Okay, here it is. Alright, so what really happens when you navigate to a URL? As a software developer, you certainly have a high-level picture of how web apps work and what kinds of technologies are involved. The browser, HTTP, HTML, web server, request handlers, and so on. In this article, we will take a deeper look at the sequence of events that take place when you visit a URL. Number one, you enter the URL into the browser. It all starts here. So in this example, they're going to facebook.com. Number two, the browser looks up the IP address for the domain name by referencing its DNS server. The first step in the navigation is to figure out the IP address for the visited domain. The DNS lookup proceeds as follows. Browser cache. The browser caches DNS records for some time. Interestingly, the OS does not tell the browser the time to live for each DNS record, so the browser caches them for a fixed duration. Varies between browsers, 2 to 30 minutes. OS cache. If the browser cache does not contain the desired record, the browser makes a system call, get host by name in Windows. The OS has its own cache. Router cache. The request continues on your router, which typically has its own DNS cache. ISP DNS cache. The next place checked is the cache ISP's DNS server with a cache naturally. Recursive search. Your ISP's DNS server begins a recursive search from the root name server through the .com top-level name servers to Facebook's name server. Normally, the DNS server will have names of the .com name servers in cache, so a hit to the root name server will not be necessary. Here is a diagram of what a recursive DNS search looks like. So we've got two sides of the diagram. On the left, we've got a box that says DNS recursor, and it's trying to get the IP address for wikipedia.org in this case. So where is wikipedia.org? Number one, it'll try the root name server, which in this example looks like it doesn't have it. It's telling you to try this IP here, .111.1, the last 2 octets. Okay, okay. I guess I don't really understand this diagram. I don't understand what this IP is. Is that, so let's see here, recursive search. Your ISP's DNS server begins a recursive search from the root name server through the, okay, it's just the IP of the root name server. Okay, so it's saying, where is Wikipedia? Well, try accessing it here. So it'll try, oh, no, that's not what it's saying. Yeah, I think I was right. It's saying, I don't know where it is, try asking this. Okay. I don't know where it is, try asking this. I know where it is, it's here. So, and of course, if it has it, it will just tell you it's at here if it knows it at the root. Otherwise, it'll go down to the .com top level, and then all the way down to the name server record. And I remember this I'm reaching way back when I went to networking school, but these are AAA DNS records. Yeah, so this was a while for me, but this is exactly the kind of thing that I'm going to be covering in this series. Kind of the things that I learned in networking school 5 years ago, and need to kind of refresh on because because the idea of this series is real world networking, to just familiarize and refresh myself with so that I'm more prepared with seeing a wider variety of things having to do with networking in the real world. So a review of DNS record types is definitely in order. So yeah, remember we've got A address records. So you've got different kind of DNS records, and I remember in networking school it was the A address record, and I think that's what they're talking about here. Yeah, but that gets really yeah, but let's try to get through this whole router before this whole article before going too deep into any tangent. One worrying thing about DNS is that the entire domain, like wikipedia.org or facebook.com, seems to map to a single IP address. Fortunately, there are ways of mitigating the bottleneck. Robin Dns is a solution where the DNS lookup returns multiple IP addresses rather than just one. For example, facebook.com actually maps to 4 IP addresses. Load balancer is the piece of hardware that listens on a particular IP address and forwards the requests to other servers. Major sites will typically use expensive, high-performance load balancers. Geographic DNS improves scalability by mapping a domain name to different IP addresses depending on the client's geographic location. This is great for hosting static content so that different servers don't have to update shared state Anycast is a routing technique where a single IP address maps to multiple physical servers. Unfortunately, Anycast does not fit well with TCP and is rarely used in that scenario. So it sounds like it would be used with UDP, which DNS typically is served on UDP port 53. Yeah, standard port 53. So it's usually UDP anyway. So I'm not sure why. But as I said, we're going to be going off on a tangent later. For now, we're just going to get through the article, and if I ever need to go off on a tangent, we'll just save what it looks like is the good thing to look up, and we'll look it up later. So let's keep my notes in order here. So we'll sort this out. So as we go through this article, we'll sort things out. So we're already learning about DNS right now. So I've got 2 articles here, in addition to the article we're reading now, that are going to be helpful for learning about DNS. Okay, so we'll keep reading and then come back to those as the next step after we're done with this. And as we go through this, we'll write down more protocols and concepts and add more links that way. And a lot of this I already know. It's just managing DNS records, that sort of thing. I haven't done since networking school. So that's the point of this series, is to practical real world networking, anything like that. This series is going to go over, and DNS very much falls within that purview. All right, so most of the DNS servers themselves use Anycast to achieve high availability and low latency of the DNS lookups. Okay. Perfect. So yep, here the first thing that happens when you navigate to a URL is you enter your URL into the browser, or you click a link and it does it for you automatically. And then the browser looks up the IP address for the domain name, and it does that using DNS. So we'll come back when I'm finished reading this and look more into DNS. But now we're going to look into the next thing that happens, and that is the browser sends a HTTP request to the web server. And now if we're talking about real-world practical networking, we actually jumped ahead quite a bit here, and I'm not sure if they're going to talk about that. They're not going to talk about that. So yeah, if we're talking about real-world practical network engineering, which, I mean, we are, that's what this series is. This is the first video in the series. There are some extra steps that belong here, and that is layer 2 and layer 3. And actually, they would even be, depending on how you are getting DNS, they would even be before, like, as part of this first step, as part of looking up the IP address for the domain name. So yeah, we'll be discussing that, layer 2 and 3 basics, and the kind of topology that you might be sending your traffic over. If you're, for instance, at a workplace with like an enterprise network, which is going to look quite a bit different than at home. At home, it's just going to be a real simple topology going right to your ISP. But if you work at a hospital or you're like at a cash register at a store, it's going to be through a much different network, and it'll have layer 2 topologies that are designed to allow for failure scenarios. And that's another thing that we'll be going over here. So yeah, so these are all the things I had planned to go over as part of this curriculum. We're not going to get through all of them in this one video, but there will be multiple videos. This first introductory video is just going to be about an hour long, and I'm just going to get through this blog. So as I said, let's not get distracted. Let's get through here, and we'll keep track of things that need to be gone through. So I'm going to do that. I'm going to say because we know that yes, the DNS lookup, the HTTP request, those are definitely things that are going to happen when you connect to when you navigate to a URL. But there's more than just what you see here. If we're talking about network engineering, which we are, so I will include that as well. And what is going to be there is all of this sort of stuff. So layer 2 and 3 basics, routing, and then topology. So let's put that here. So we're going to say layer 2, 3, and we'll say routing. We'll say ARP scaling. We'll say topologies. You can even have the first hop redundancy protocols there as well. Even hardware, the kind of equipment, and this will be like wireless access points as well, edge, core, different layers of your network, depending on where you are or what you're connected to. So yeah, okay. Okay, and I'm gonna put design, because that's something I definitely want to talk about as well as part of this series, is designs and trade-offs. So we'll just put the term designs and trade-offs here. And we've already got some designs and trade-offs listed here. Just off the top of my head, without looking at it, we've got the little Anycast versus the other ways of addressing your server. So let's review that again. I can't remember off the top of my head. Yeah, so we've got Robin Dns, we've got load balancer DNS, we've got Geographic DNS, and we've got Anycast DNS. So yeah, and that's because all your DNS entries are going to come to a single IP address. So you need some sort of mechanism to make sure that you're not bottlenecking your whole, so that when you navigate to a URL, this process of getting back the number IP that corresponds to, for instance, facebook.com, wikipedia.org, is timely. It doesn't take longer than a user can wait. So if you just have it mapped to a single IP address, then that single IP address is responsible for too many requests, and you add to that delay time, and you reduce the usability of the internet. So the ways you can mitigate that and have multiple IP addresses serve DNS requests, thereby reducing that delay in resolution for the name, getting the IP of the name, are Robin Dns, Load Balancer DNS, Geographic DNS, and Anycast DNS. So let me write that down. So Robin DNS, load. So I'll just say Robin load balancer, geographic, and the final one is Anycast, and that's one I'm more familiar with. This is the one I have seen implemented in my experience, but as I've mentioned, the point of this series is real world networking in the wild. So we'll be discussing all four of these because all four of them very much will pop up. So the first one is Round Robin DNS. It's a solution where the DNS lookup returns multiple IP addresses rather than just one. And an example of that is facebook.com. Maps to 4 IP addresses. I believe Google also maps to multiple IP addresses. So let's take a look at that actually. Let's go to google.com. And then we'll open up the, if I hit F12. Yeah, so I've got F12 open here. So now we've got this console. We can see all of the source code of the page. We can see a console tab here, so we can see any error messages that the page came back. We can see sources. So like if the page has like images on it, if it has JavaScript, so like if the JavaScript is for the page to do things like an animation or take input or something like that, it'll have a JavaScript file with these functions in here. So when you click on something, something happens. You can do that with JavaScript. And then, yeah, so we'll have all sorts of things. You've also got a network tab on here. So now this is what I'm going to be focusing on. You can see what sorts of things were transferred throughout in the network, and the reason I want to focus on this tab is because when you click on one of these things, you can see the header of the request. So we didn't talk about these yet. So before I move on, well we're in the middle. That's because we're in the middle of talking about this. I wanted to show that Google uses multiple addresses. So here we can see one of the addresses that Google is using, this 216.58.194.97. That's an address that belongs to Google. I can prove that by going to whois lookup. Yep, so whois DNS lookup. There's many to use. You can use Oops, that's a domain name. So, but yeah, so I can't. Yeah, I can't put in a. But let's try with Google.com, and we'll probably see that IP address pop up. Oh no, I don't see it. Oh, sorry. It's not going to be a. It's not going to be a who is. It's going to be a SWIT. Yeah. So this Aaron.net here. Oh, it is going to be a. It is going to be a who is. So. Okay, yeah, I guess that other one just wasn't accepting number IPs for some reason. That's unusual. Usually it accepts number IPs. That's why I didn't think I was using the right thing. But I was. It's just the search engine I was using was unusual. It was more limited than this one. This is a much better place to look this up. But yep, we can see that this address belongs to Google. So if I were to refresh this, yep, here's google.com. There we go. So we've got a different address now, but we're on the same page. Let's try it again. So looks like we got the same one this time. Let's just keep refreshing it until we get a new one. Right now we've got 172.217, which is of course a public IP. The private IP range is .16 through .31. So it goes from, it's a /12. It goes from 172.16.0.0 to 172.31.255.255. So .271, that's a public IP. And that's just one of the IPs that Google has. I should get, you know what, it's probably cached now. That's probably what's happening. Like they said that on there, that it's in my browser cache. So I think I can do like Control R. Yeah, and then I can refresh it and get rid of my cache. I'm pretty sure that will work. Another thing I can probably do is go into incognito mode. Because I think it's using a cached entry for it, so it's not going to give me a different. And we saw that in the blog post. So what really happens? First thing it's going to do is look at your browser cache. So it's not going to give me a different address to Google because I've already got one in my cache, and that is the only one that I need. But for the purposes of demonstrating the fact that Google actually does have more than one address, you can see here I opened up a incognito tab, which isn't going to save a cache. And sure enough, now I've got a new address for Google, 142.250.138.103. That's different than the first address I had, 172.217.14.164, and that's because there are multiple DNS. There are multiple addresses for Google instead of just one address to prevent that bottleneck. So DNS can resolve faster. Okay, and I doubt they're using round robin, but we can see they're not using Anycast. We're getting more than one IP. So I would guess that they're using so major sites will typically use expensive high performance load balancers. So yep, this is what I would predict that they are using, which is a load balancing. It's the piece of hardware that listens on a particular IP address and forwards the requests to other servers. Major sites will typically use expensive high-performance load balancers. The next type is Geographic DNS. It improves scalability by mapping a domain name to different IP addresses depending on the client's geographic location. This is great for hosting static content so that different servers don't have to update shared state. And the last one is Anycast. And it's a routing technique where a single IP address maps to multiple physical servers. Fortunately, Anycast does not fit well with TCP and is rarely used in that scenario. So, load balancer I think is the big one, but we have seen that yeah. Yep, so we've seen that there are multiple IP addresses for Google, but I don't think that means that it's round-robin DNS. It just means that that the load balancer will forward it to the other servers, and there's more than one server that it can be forwarded to. Okay, so the next step is the browser sends a HTTP request to the web server. And that's what we were looking at here to get our remote address. So we can see the request is a GET. Status code was 200, so it was successful. We've got various other headers here, but let's read the blog. You can, and we can see here it's a GET request as well. You can be pretty sure that Facebook's homepage will not be served from the browser cache because dynamic pages expire either very quickly or immediately. Expiry date set to past. So the browser will send this request to the Facebook server. Yep, so this looks very familiar. This is what we have here. This is the GET, and this is what the browser is sending. So we can see that the host that it's sending it to, in this case, is Facebook, but the host value here will be I guess I don't see the host value on this one. It must be okay. Well, it looks a little bit different, but I think it's the okay. This request URL, that's going to be. I don't think they'll have. They don't have request URL anywhere on here. So okay, but you can see we've got user agent. They're using Mozilla, so it's going to look quite a bit different because all of these are just what they're all standardized. They're all the same across browsers. It's just your browser might show it to you a little bit different than another browser, even though it's the same information. How it's presented depends on how the programmers who build the browser choose to present it. And we can see it's a little bit different across Firefox and Chrome. And they are using Mozilla here for their user agent. My user agent is going to be different. It's going to be Chrome. Oh, actually no, I was completely wrong about that. Okay. Well, that's not good. Okay, well, I don't know what a user agent is then. All right. Well, anyways, let's try to get through this here. I'm already at the 35-minute mark, and I'd like to only spend an hour on this first video. And I've only made it to number 3, and it looks like there's 10 numbers. So I should be at past number 5 right now if I want to finish this in an hour. The GET request names the URL to fetch, Facebook http://facebook.com. The browser identifies itself, user agent header, and states what type of responses it will accept encoding headers. The connection header asks the server to keep the TCP connection open for further requests. The request also contains the cookies that the browser has for this domain. As you probably already know, cookies are key value pairs that track the state of a website in between different page requests. And so the cookies store the name of the logged in user, a secret number that was assigned to the user by the server, some of the user's settings, etc. That is what's stored in a cookie. And cookies are our key value pairs. So let's look at a cookie here. So here's we're setting a cookie here, some key value pairs. I'm surprised it's showing up like that. I thought it would be like more clear that it was like a cookie. Usually when and I don't see the key, I see the key value pairs now. So the key is in capital letters here. So we've got the consent key, the HSID key, the SSID key, all the way down to the final key here, which is the underscore. Oh, that's interesting. Oh no, this is the key. Underscore, capital S, lowercase e, C, U, R, E, because we can see the equal sign there. So let's put this in a bit of an easier place to read. It's, I think, kind of hard to tell that that's an equal sign. So I'm going to put this in Notepad++, and we're going to look at this more closely. Okay, so now it looks a little bit more clear here. We can see the equal signs. I can even double click them and mark them, and then they'll really jump out. Yeah, so now they're jumping out a lot more. So we can see, yep, sure enough, each of these here are key value pairs separated by this colon here. And then, the key and the value are separated by the equal sign, but each key value pair is separated by the colon here. And then we can see we've got the consent key, HSID key, but they're not all as simple as that. Some keys look like they're quite complex in their syntax, and we've just got a number of keys here. Some values look very complex. So yeah, that's it. It's like nothing. I haven't really looked too closely into cookies like this yet. As a network engineer, I'm usually on routers and switches instead of the browser. Usually not on like a web browser, but I've definitely looked at the web browser tool that I got this from a lot, because it's just a wonderful tool, I think. And yeah, we can see on that tool is just the cookie here, and yeah, so let's keep reading the blog. The connection header asks the server to keep the TCP connection open for further requests. So let's see if we've got a connection header. So here's the request header. I don't see anything about connection. I don't see a connection header. Huh, why is there no connection header? Connection, keep alive. Yeah, there's no connection header. Now this is the response header. Yeah, so we gotta look at the request header for the keep alive. Huh. Is it part of the cookie? No, it's not. It should be by the user agent. We do have a user agent, yeah, right here. But that's interesting. I don't see the connection header. Is there a way to search for it? Let's see here. So maybe I can filter. What was that? CONN? I don't know what that means. Okay, I guess I'm surprised I don't see a connection header. It looks quite a bit different here than it does there. There's no keep alive connection header. Maybe there is in the incognito tab. Nope, they still don't even see it there. Okay, so, well, no match is found. Alright, so I'm not sure why it's not showing up there, but maybe because it's just not keeping the TCP connection open for further requests. It's making a new connection every time. But the TCP connection, that's a three-way handshake process. Hopefully that will be mentioned here. Alright, so the request also contains the cookies that the browser has for this domain. As you probably already know, cookies are key value pairs that track the state of a website in between different page requests. And so the cookies store the name of the logged in user, a secret number that was assigned to the user by the server, some of users' settings, etc. The cookies will be stored in a text file on the client and sent to the server with every request. There's a variety of tools that let you view the raw HTTP requests and corresponding responses. My favorite tool for viewing the raw HTTP traffic is Fiddler. but there are many other tools. For example, Firebug. These tools are a great help when optimizing a set. I'm curious when this was written, because it was written February 9th, but what year? Let's see if there's anything in the, like the, yeah. So, is there anything in here about like what date this was written? No, I don't see anything. Let's try to be nice if I could just expand all. Okay, well, anyways, I was curious when this was written, because I think, oh, here we go, here's some comments. So, okay, I think it was written probably this year. The other thing I can do is do a, I really like this tool here. You can click this arrow sign like that, and then you can click anything on the page and it will tell you, okay, so there really isn't anything about the year here. Yeah, I'd really like to know what the year is that this was written. I mean, hopefully it was written this year, but I'm wondering if it was written a while ago, because I've never heard of using like Fiddler. Like I typically use just this built-in tool in Chrome. Yeah, and I'm just wondering, yeah, we can see here Firebug is discontinued. So yeah, it looks like, we can see that the last stable release was 3 years ago. So yeah, I'm guessing that this article was written probably like 3 years ago. Yeah, I just like the F12. Like I think this is enough, because you can see the raw HTTP requests and corresponding responses here by just going to the network tab and then getting the, yeah. So now here's the requests and the responses, and you can narrow it down based on it being a request or being a response as well, I believe. I'm not sure how to do that. Just off. Oh no, here it is. Oh no, never mind. Shoot. Filter. So yeah, I'm pretty sure you can filter it. Oh, so anytime you have a request, you're going to have a response. Or if you don't have a response, you're going to get an error message. And we can see here we got an error message. We got a 404. So the requests are here, the responses are here. So you won't have you won't be able to filter out all of these for request and response, because a request is always going to have a response, even if it's just that it didn't get a response. So there's no way to. It's not like a Wireshark capture where you can filter it based on the source IP, because that's not what we're talking about. We're talking about we are kind of talking about that because we're talking about the request versus the response, but each request will have a response. So we don't need to filter out the requests or the responses. So yeah, here we can see the raw data. I think you can even get it so that it's just completely raw. Yeah. So here, oh no, that's the response that we got back. Oh, here's the values of the cookie, really nice and laid out. But yeah, this tool is plenty. You don't need to use some special tool. Chrome, Firefox already have it. It's typically just F12. In addition to GET requests, another type of requests that you may be familiar with is a POST request, typically used to submit forms. A GET request sends its parameters via the URL. For example, this URL here, and let's take a look at that. So I'm gonna get rid of all of this, and I saved this. Now here's an RFC that I don't need to look at that. Get rid of these. So yeah, let's go to this URL. But before I hit the enter key, let's make sure that we've got this running, and let's clear it out too, so that it's not cluttered. Okay, so we've got this recording here. So we're going to record our network activity, but right now we don't have any. Maybe we'll have like a keep alive or something popping up. Don't see one yet though, but we'll have a bunch of activity once I hit enter. There it is. And now we should see a POST request as well as a GET. So I don't see any difference between GET and POST just off the top of my, just at a glance. But let's try filtering. Okay, that doesn't work. I mean, we'll have to click into it. Okay, we've got a GET, another GET, another GET. Okay, I don't see any posts right away. A POST request sends its parameters in the request body, just under the headers. So let's first of all take a look at the page here. Okay, so puzzle 85, less or more. You should see a post. I think there's a better. Yeah, let's use a better page to learn about POST requests. So, yeah, W3 Schools is a really good page for that. So there should be an example where we can make a, yeah. So like, yeah, when you send data to a POST request, you just send data to a server to create or update a resource. So typically, that is really, really locked down and secure, because you can, if you're able to update or create a resource on a server, you might be able to do things that the administrator of that server does not want you to do. So where you can and cannot do post requests is often very, very well restricted and designed, and often not, and that's where security comes into play, making sure that those post requests are handled the way they are intended to be. So yeah, I should see a post request if I mean, these are just GET requests for another page. I believe, yeah, these are all just GET requests. But a post request, yeah. So like if I do this do it yourself here, and I hit run, I should see a post request. Oh. I don't see one. Huh. Okay. Yeah, I think it's a little bit different than what I was expecting. I thought it would. Let's try to see a post request. So. I mean, I know like a so yeah, let's do this. So API tutorial. Okay. Yeah. So here we go. So REST API tutorial. Perfect. So now we can do a. Oops. They should have a. Well, let's do this. So cat API. So we should. There. Yeah. So here we go. So the cat API. Cat as a service. So now we can send a post request to this, and we can get cat images back. But it looks like this they want you to pay for it, so we can do Pixabay API. There we go. So now, yeah, pixabay.com. We can go to, search images. Okay, so here's the Pixabay API. So now we can do a post request. Well, a post request would be like adding an image to the server, and they're not going to let us do that because then there won't be. Yeah, so it's like uploading something. Yeah, it's not super easy to demo a post request because, as I mentioned, that can leave a server vulnerable to security flaws. Okay, so the trailing slash in the URL, http:// is important, or in this case, the browser can safely add the slash for URLs of the form http:// example.com /folder or file. without a forward slash, the browser cannot automatically add a slash because it is not clear whether folder or file is a folder or a file. In such cases, the browser will visit the URL without the slash, and the server will respond with a redirect, resulting in an unnecessary round trip. Okay. All right. I'm not sure why this is mentioned. If there's a way, if they're recommending a way to have your URL so that it doesn't, like, I'm not sure why they're saying it's an unnecessary round trip. It sounds like the round trip is necessary so that it knows whether it's a folder or a file, but they are including that word in there for a reason, but not explaining what that reason is. But let's just keep on going. Number 4, the Facebook server responds with a permanent redirect. And this is 301. I think we saw a 301. Let's look at our, yeah, so did we see a 301? I thought we did. We saw a 307. Oh, here we go. Here's a 301. So we did see a 301 from the disk cache. This is the response that the Facebook server sent back to the browser request. 301 moved permanently. The server responded with a 301 moved permanently response to tell the browser to go to http://www.facebook.com instead of http://facebook.com. All right, so let's try that and let's see if we get that redirect. Let's try going to Pixabay again. And we'll see if Pixabay has that. So let's see if we get a 301 if I refresh this. I got a 302. Lots of 302s. I don't see a 301 though. Let's see what we get for Facebook. And we'll go to HTTPS instead of HTTP. Okay, so here we got the 301, which is a redirect, and you can see it put the www in there, even though I didn't originally include it. All right, moving on. There are interesting reasons why the server insists on the redirect instead of immediately responding with the web page that the user wants to see. One reason has to do with search engine rankings. See if there are 2 URLs for the same page, say these 2 URLs. Search engine may consider them to be 2 different sites, each with fewer incoming links and thus a lower ranking. Search engines understand permanent redirects, 301, and will combine the incoming links from both sources into a single ranking. Also, multiple URLs for the same content are not cache friendly. When a piece of content has multiple names, it will potentially appear multiple times in caches. And that could fill up your cache, because caches are a limited storage space. All right, so the next thing that happens is, so this is what happens when you navigate to a URL. First thing is DNS. Second thing is HTTP. And then of course there's layer 2 ARP tables, all that sort of thing. Then there's the redirect if it's not the main page they want you to go to. And then it's following the redirect is the next step. The browser now knows that http://www.facebook.com/ is the correct URL to go to, and so it sends out another GET request in order to go to that. So we've seen that. Let's look at that one more time. And this is what we saw. So let's go facebook.com, and we can see we've got that 3 to 1, but now we've got the other get to go to www.facebook.com instead of just facebook.com, and that's where we've been redirected to automatically. So before we even get a result back for facebook.com, we're redirected to www.facebook.com, but you can see it did actually accept facebook.com into the browser. It just immediately adds the www because that is the website that it is actually meant that it knows you want to go to. So it redirects you to this because this is the site that they're going to, even though they have both sites available, this site is just essentially a kind of like a traffic controller, directing the traffic, the plane over to the other runway, because they're going to use this in the cache and in all their search engine optimizations, everything like that. They're using the www.facebook.com instead of just facebook.com. So anything that goes to facebook.com, you just get this redirect and you send out another GET, and then you land here, www. Okay, so the meaning of the headers is the same as for the first request. All right, so the sixth thing that happens is the server handles the request. The server will get the GET request, process it, and send back a response. This may seem like a straightforward task, but in fact there is a lot of interesting stuff that happens here, even on a simple site like my blog, let alone a massively scalable site like Facebook. So one of the things that happens involves the web server software. The web server software, for example IIS or Apache, receives the HTTP request and decides which request handler should be executed to handle this request. A request handler is a program in ASP.NET, PHP, Ruby that reads the request and generates the HTML for the response. So this is in the OSI model. This would be layers 6, 7, and 8 we're learning about right now. Definitely important to learn about. It's what it's a part of the OSI model. My professional experience has mostly been in the lower layers, layers 2 and 3, a little bit of layer 4, but this is definitely part of this series, real world, everyday network engineering. So this is the perfect thing to be learning about. In the simplest case, the request handlers can be stored in a file hierarchy whose structure mirrors the URL structure. And so, for example, this URL will map to the file http docs folder 1 page1.aspx. Yeah, I remember this from networking school. This was a while ago though. But yeah, so this domain is for use in illustrative examples and documents. You may use this domain in literature without prior coordination or asking for permission. So let's take a look at it under the hood, and we'll capture the requests. So, oh, it looks like there is no. Okay, so we're trying to get this page 1 here, and for some reason we didn't get page 1. That's interesting. That's interesting because like I see something there, so I'm surprised that we're not getting anything. You know, if I see something here, like, yeah, that really surprises me that I've actually am seeing anything here if it's a 404. Okay, but let's keep on going. So the web server software can also be configured so that URLs are manually mapped to request headers. And so the public URL of page1.aspx could be this URL here. So you don't have to include the .aspx on it, even though that's the file you're accessing, page1.aspx, because instead of making the user specify the file extension, you can configure the web server software so that the file extension is manually mapped to the request handlers, so that the URL knows that it's an ASPX file without the user telling that. So you can say, when you go to this URL and you go to page 1, page 1 is an ASPX file, and that's the way it is. But if you don't do that, of course, and you don't include, and the user doesn't know what kind of file it is, they think it's a PDF, they go to page1.pdf, they're going to have problems. So that makes it a lot easier on the user. They don't have to know what kind of file they're accessing. They just need to know the name of the file they want to see. And then the administrator of the server can set up their request handlers so that the type of file is automatically mapped, and the person accessing the file does not need to know what type it is. Okay, so, and that leads us to the request handler. The request handler reads the request, its parameters, and cookies. It will read and possibly update some data stored on the server. Then the request handler will generate a HTML response. One interesting difficulty that every dynamic website faces is how to store data. Smaller sites will often have a single SQL database to store their data, but sites that store a large amount of data and or have many visitors have to find a way to split the database across multiple machines. Solutions include sharding, or splitting up a table across multiple databases used on the primary key, replication, and usage of simplified databases with weakened consistency semantics. One technique to keep data updates cheap is to defer some of the work to a batch job. For example, Facebook has to maintain the news feed in a timely fashion, but the data backing the people you may know feature may only need to be updated nightly. My guess, I don't actually know how they implement this feature. Batch job updates result in staleness of some less important data, but can make data updates much faster and simpler. So the seventh thing that happens when you navigate to a URL, and of course this is just what this blog is saying, and it's focusing more on the upper layers of the OSI model, which is perfect because I know more about the lower layers, so it's really good that I have a refresher on this, because when it comes to layer 2 and that sort of thing, I'll be able to just offer that myself instead of having to rely or instead of having to have a blog like this jog my memory. So, and we'll get into that eventually. Right now I'm just focusing on getting through this blog. But the seventh thing is the server sends back a HTML response. And this is 200, assuming everything goes good. Here's the response that the server generated and sent back. 200, okay. So the other thing that's important to know about is HTML response codes. And it can tell you it's a teapot. I forget which one that is, but there's lots and lots and lots of response codes. There are ones that not all are used equally as much. There are only a few that are used often. The rest are used in special circumstances. But yeah, what's the I'm a teapot one? Yeah. So this will tell you if oh, but it's not actually, yeah, 418, so they won't actually tell you. But yeah, let's save this, the list of HTTP status codes, and we're going to keep this in our notes. Yeah, so here we'll make a checklist for that, and we'll just have an empty checklist, or an empty list of bullet points. And then the next part is HTTP. But here we'll include the list of codes, and then we'll include the Wikipedia page on HTTP, although we're getting a pretty good explanation of it, I think, just in this blog itself. But the purpose of those notes are to get more information. Yeah, so this is really good. Okay. All right, and that's what we're still focused on, is the HTTP portion of this. The entire response is 38 kilobytes, capital B for bytes. At the end that I trimmed. So he trimmed off this. This is the bulk of the response. The content encoding header tells the browser that the response body is compressed using the gzip algorithm. After compressing the blob, you'll see, after decompressing the blob, using something to unzip it, because we can see it is zipped using the gzip algorithm, you'll see the HTML you expected. Okay. In addition to compression, headers specify whether and how to cache the page, any cookies to set, none in this response, privacy information, etc. So let's take a look at some headers again, and let's see if it's compressed. So they got a 200 back, and they've got content encoding. I've got a 200 back. Yep, and this is my general headers. We've also got response headers, and we've got request headers. They give the response headers first because I think that's because they assume you want to see the response. I don't see anything about compression. Yeah, I don't see anything about compression there. All right, moving on. Notice that the header sets content type to text/HTML. The header instructs the browser to render the response content as HTML instead of, say, downloading it as a file. The browser will use the header to decide how to interpret the response, but will consider other factors as well, such as the extension of the URL. So it's going to tell here, aha, content type text URL, that's certainly going to be involved. Here, perhaps it's just not zipped, is why we didn't see it, the zip here, but we're certainly going to see the content type because we received content, and it's certainly going to be text HTML because we have text HTML. We can see it right here. Okay, so the next step is the browser begins rendering the HTML. Even before the browser has received the entire HTML document, it begins rendering the website. Wow, I didn't know that. I actually thought that it received the whole thing and then it rendered it. So that's interesting that it can do it before it even has the whole document. I did not know that. Next step, step number 9, the browser sends requests for objects embedded in HTML. So the browser is going to get the GET request, and it's going to, in addition to that, request for embedded objects. As the browser renders the HTML, it will notice tags that require fetching of other URLs. The browser will send a GET request to retrieve each of these files, and we can see it does that. You know, that's one of the main things it does. Like, look at how many other things it had to get. Like, you know, every single page. When you go to a page, you don't just go to a page. You go to pages upon pages upon pages. So, and we can see that here. Look at all the things I needed to get. I needed to get analytics files. I need to get SVG files, JavaScript files. I'm sure there's an image somewhere that I needed to get. Yeah, like this image right here. I'm sure I needed to get. Let's see what this is. So this is. Huh. Alright, well, I don't see it. But we can see here content type, so if there's an image, it will show up as a particular content type. Ah, here we go. So SVG, these are, yeah, so this is probably an SVG image file. So image, that's what these .svgs are. I was expecting to see like a PNG or something like that. Ah, here we got one. But yeah, I didn't know that SVG was a type of image. Here are a few URLs that my visit to Facebook.com retrieved. So we got some GIF images, probably like the Facebook logo. Let's take a look at what this is. Oops, so that's not, yeah, but in our case, when we went to this help page, we got this URL here. So let's see. So in the request header, so here it is. Here's the request header. Provisional headers are shown. Disable cache to see. Okay, yeah, because we're in the cache. So let's go to like a good website, and we're gonna be in incognito mode, so we're not looking at the cache. So we'll go to like cats.com. I hope. Well, let's search it in Google in case it's not a. Yeah. So. Okay, here we go. So we got some cat images. So we'll open this up. And now that we're recording, oops, it looks like we got like a keep alive message, something like that. Oh, we got a post now. Yeah, I'm not sure what this is about, but if I refresh, now we're gonna get all sorts of things, and we'll see yep, we've got all our JPEG images here. So, oops, we've got provisional headers still. It looks like we've still got a cache, even though we're in incognito mode. So, yeah, we're not getting the actual. But if I go here, now we can see what I was looking for. So this is the source of the data. It's not where, as we saw, that's not where it's actually accessing the data. It's accessing it from the cache, but where it actually sits is here. So yeah. So now we see the actual image here because this is the URL for that image, but the image is cached, so we're not going to be accessing it via a URL. We're going to be accessing it via the cache. Okay, and then of course it's got style sheets, change everything. It's got JavaScript files for interactivity. Each of these URLs will go through process asimilar to what the HTML page went through. So the browser will look up the domain name in DNS, send the request to the URL, follow redirects, etc. However, static files, unlike dynamic pages, allow the browser to cache them. Some of the files may be served up from cache without contacting the server at all. The browser knows how long to cache a particular file because the response that returned the file contained an expires header. Additionally, each response may also contain an etag header that works like a version number. If the browser sees an etag for a version of the file it already has, it can stop the transfer immediately. So let's see if there's an etag? ETH? Does that show up anywhere? ETag? I don't see one. Search for cats, maybe? ETag? No, I don't see one. So, I mean, there should be ETags for these, right? Because I already have them. Yeah, I guess I'm not sure what they're talking about there. Alright, so this is to serve it up from the cache. However, static files, unlike dynamic pages, allow the browser to cache them. Some of the files may be served up from the cache without contacting the server at all. The browser knows how long to cache a particular file because the response that returned the file contained an expires header. Additionally, each response, so let's take a look at the response. So let's take a look at the response for one of these images here. So they're going to be perfect. So yeah, here's the one of the images. So let's look at the response headers. And it's to the cache. Yeah, so it's a provisional header because it's accessing it from the cache already. Yeah. Okay, so we're not seeing a large part of what they're discussing there because it's accessing it from the cache. What is being discussed here is the initial process of caching the file. The browser knows how long to cache a particular file because the response that returned the file contained an expires header. Additionally, each response may contain an etag header that works like a version number. If the browser sees an etag for a version of the file it already has, it can stop the transfer immediately. So we should see in here, especially as I scroll down, we should see some of these images start to populate. I wish I could close this out. What if I? Okay, so if I scroll down, yeah. So we're getting some new images as I scroll down. So we should see. Yeah. So we've got new images that I haven't seen before coming in as I'm scrolling down. So now we should have an expires in our response, not in our general. Aha, so we've got it right here, and now it will be in the cache. So if I were to refresh, we won't get this one again the way we got it this time because we'll be getting it from the cache. But we didn't have this one in the cache before. Let's see. Yeah, we didn't have it in the cache before. But you can see, first of all, we've got these. I'm not sure what these are. But as I showed here, when we get new images showing up here, they'll be showing up down there. So as I scroll down, yep, see all those images coming in? That's because we haven't seen them before, so we're pulling them from the network. But if I refresh the page and I go down, I believe they're going to look a little bit different now because they'll be coming from the cache. No, it looks the same. But anyways, the important thing to know is that you can look at the response headers through this console here, and you of course won't be able to look at those response headers until you send a request. Yeah, it looks like it is requesting to the cache. Oh yeah, so we gotta look at the request headers. So let's focus on the request headers and search for dogs. So yep, we've got plenty of dogs showing up now. So let's focus on the request headers. So we've got provisional headers, but as we get new photos popping up here. Yep, so we got a new dog photo here. Aha, so now we've got a request header that isn't from the cache because we've never seen this photo before. It's not anywhere in the cache. Yep, and as we're getting more, the request headers, yep, we can see they're not coming from the cache anymore. They're coming from this path here on the server. Yeah, the refer google.com/. So we can take this and see the photo. So if I were to go like this, copy value, open a new one, paste it in, and then of course that copy value, and then So this is the server that's actually serving it up, this google.com. This is the path where it is on the server. Enter, there we go. We got the picture of the dog that came in. So, yep, and we can see as we scroll down, we get, as we scroll down here, to get more pictures of the dogs, more pictures are coming in. But if I were to refresh the page, now as I scroll down and I look at the request headers, we're going to see those abbreviated headers. So as I scroll down and we got more coming in. Yep, so we got some more coming in. These are now provisional headers because we've already seen those images, so they're in the cache. So we don't have to request from this actual Google server here. We can just request from our own cache and we can get it faster. We don't have to get it from California. I'm in Texas, so that's a long ways away. We can just get it from our own device, which is right here in the room with me, and it's a lot faster, a lot better in every single way. All right, so we're almost done here. It looks like I lost my camera. Let me try to get that going again. I apologize for that. I know that happens a lot. It just stops and starts. Okay, so let me hit deactivate and activate. Okay, my camera's back, so let's keep going. Can you guess what fbcdn.net in the URLs stands for? A safe bet is that it means Facebook Content Delivery Network. Facebook uses a content delivery network, CDN, to distribute static content, images, style sheets, and JavaScript files. So the files will be copied to many machines across the globe. Okay, let's look at that. So we should see any image. So let's go to a Facebook post for juggling. So here we go. We've got the IJA book or IJA Facebook page. So as we scroll down, we'll get some new images, and it should come from a special server that serves up those images. So now we're getting. But the thing is, we're not logged in, so we're not able to see any of those photos until we log in. But it looks like here's a GIF. Oops, but it comes. Yeah, this we've seen before. So yeah, I think it's different. I think we're not seeing that because we're not logged in here. Oh no, here we go. So here's fbcn.net that we're still requesting the Facebook, but we got this authority here. So static content often represents the bulk of the bandwidth of a site and can be easily replicated across a CDN. Often sites will use a third-party CDN provider instead of operating a CND themselves. For example, Facebook's static files are hosted by Akamai, the largest CDN provider. So obviously this is a typo here. They meant to say CDN an additional time. So yeah, content delivery network. Yeah, and that makes sense. If you've got videos, if you've got pictures, we all know. I'm fighting with disk space on my personal laptop running out. Anytime I make one of these videos, I have to delete 2 more. So you just hire a third-party content delivery provider, and they make sure there's enough space for your photos and videos, and you don't got to worry about it. As a demonstration, when you try to ping static.ak.fbcn.net, you get a response from a Akami.net server. Also, interestingly, if you ping the URL a couple of times, you may get responses from different servers, which demonstrates the load balancing that happens behind the scenes. Okay, so let's try that. Oops, so it cannot find that. Okay, I'm not sure why it can't find that. Oh, it's just not. Maybe they no, that's correct. What's this? Let's try going here. Okay. All right, yeah, let's try this. So let's see if we get a response from a Akami server if we just ping this. Okay, so let's see if this. Okay, first of all, let's do a -C1 to only get one response. Oh, I need administrative privileges apparently. Let's ping it a few more times, see if we get a new new IP coming back. Nope, it looks like we're getting .35 each time. So I don't see anything involved with a load balancer, but let's put this in the who is and see if it belongs to either Facebook or Akami. Okay, so it belongs to Facebook. So this looks like it's, yeah, so maybe because I'm pretty sure this was written like a few years ago. I wasn't able to find out for sure, but maybe since this was written, this has changed. Or what if I try HTTP? No, okay. Okay, so this is all different, maybe because this blog entry is a few years old. But the good news is we're very nearly at the conclusion. We're about 2 hours in. I only wanted to do an hour video, but I needed to go through all of this anyway. This is absolutely perfect. This is the exact kind of thing I need a refresher of the upper layers of the OSI model. The browser sends further asynchronous requests, or AJAX. In the spirit of Web 2.0, the client continues to communicate with the server even after the page is rendered. So the browser gives the GET request, and then the Facebook sends back XML, and then it continues to communicate. It doesn't just say, instead of saying, "How are you?" "I'm fine." You say, how are you?" And they say, "I'm fine, the weather's great, my kids are wonderful." You know, it goes on and on and on, keeps talking. So for example, Facebook chat will continue to update the list of your logged in friends as they come and go. To update the list of your logged in friends, the JavaScript executing in your browser has to send an asynchronous request to the server. The asynchronous request is a programmatically constructed GET or POST request that goes to a special URL. In the Facebook example, the client sends a POST request to the link here, and you can see we've got the .php, so they didn't set up special request handlers for that, or if they did, they're specifying this anyway. But let's take a closer look at what's going on here. So we've got a page that's not available, and that's status 404. That's what that means. So let's take a look at this closer. So here's our request to facebook.com through a GET method, and we wanted to find this buddylist.php file, but here's our response. Response, let's see here. I'm looking for the 404 response in the response headers, but I think they're only going to list it in the general headers. Yeah, so it's the status code. It looks like the status code isn't a part of the response. It's just a general code for the whole thing. I think that's kind of like misleading, like, because I'm pretty sure the status code would be a part of the response. It's probably in there if I look closely enough. I'm just not sure where. Probably in like one of these keys. Yeah, I'm sure it's got to be in the response, right? Huh. Okay, well, it's in the general general headers. Okay, so in the Facebook example, the client sends a post request to fetch the list of your friends who are online. This pattern is sometimes referred to as AJAX, which stands for Asynchronous JavaScript and XML, even though there is no particular reason why the server has to format the response as XML. For example, Facebook returns snippets of JavaScript code in response to asynchronous requests. Among other things, the Fiddler tool helps you view the asynchronous requests sent by your browser. In fact, not only can you observe the requests passively, but you can also modify and resend them. The fact that it is easy to spoof AJAX requests causes a lot of grief to developers of online games with scoreboards. Obviously, please don't cheat that way. Ah, that must be how. No, what happened? Something happened. Okay, I think it's good. Okay, nothing happened. But I liked to go to subnetting.net. And I used to try my hand at this, and I noticed that the subnetting practice leaderboard had scores on it that were far too high, and I wondered how they had done that. And it looks like they might have modified the AJAX request to do that. So let's view all of the stars. So here we go. So here's the leaderboard.aspx. So the request is here. The response we've got is a XML. So where's the AJAX request? Oh, here we go. So here's the AJAX request. So if I shrink these down, oh, okay, this came from the cache. Is there anyone that wasn't cached? This one wasn't cached. Query string. Facebook. Okay. But I'm pretty sure you can modify and send it from here. I'm security. What is lighthouse? Oh, okay. Application. Background fetch. Push messaging. Maybe that's it. Yeah, I thought you could just do it right from here. Like I can right click on this, like review, like in my response header, or like I can yeah, so I can like copy this, or I can like resend it. I thought there was a way you could just do it right from here. Let's say Google F12 console craft custom Ajax request. Yeah. Okay, so is there a way to make an HTTP request using the Chrome developer tools without a plugin? There is. So you would use fetch. You would use this fetch method. It looks like it's in there. So if I go here and I go to the console and I do fetch, there we go. So I can build my own request just right from the console using this this fetch function they have. So if I do this, boom. So I sent a special thing, and I can send my own custom Ajax responses, whatever I want, right from here without getting anything extra, as long as I know that I can use this fetch command. I wonder if there's a help in the console here the way there is in Python, because that really, what if I do help fetch? No, what if I do like info fetch? Okay, and you can see it'll tell me what's in there. So I don't see info in there, I don't see help in there, so unfortunately they don't have that. But what if I do fetch like this, and then I right click on it? No, nothing. So unfortunately it doesn't work like Python, where you can get built-in real-time on-the-fly help. But that's really my favorite thing about Python. That's one of the reasons why Python is such a great language. Unfortunately, this console doesn't have that. Okay, so Facebook, oh, yep, and don't cheat by modifying the Ajax requests, even though it's really, really easy to do that. You can just do it directly from the console line here, using the fetch function. Facebook Chat provides an example of an interesting problem with Ajax, pushing data from server to client. Since HTTP is a request-response protocol, the chat server cannot push new messages to the client. Instead, the client has to poll the server every few seconds to see if any new messages arrived. Long polling is an interesting technique to decrease the load on the server in these types of scenarios. And the server does not have any new messages. Oh, if the server does not have any new messages when polled, it simply does not send a response back. And if a message for this client is received within the timeout period, the server will find the outstanding request and return the message with the response. So in conclusion, hopefully this gives you a better idea of how different web pieces work together. Looks like skip lists are fascinating. I don't know what that is. But anyway, yeah, that's all I wanted to do for this first video on real world in the wild networking. I'll probably call this wild networking or real world networking, something like that. But there's going to be plenty of videos over the week, over the next week or so. And we'll be going through all of the topics I have here. Next video, I think we're going to be going a bit deeper into DNS, looking at the Wikipedia page, looking at this Cloudflare page. We're going to be looking more into designs and trade-offs, such as these round robin, load balancer, Geographic and Anycast designs. We'll be looking at layer 2 and 3 as well. That I know really well. So we might be saving that maybe for the end, because I don't really need to review that as much. ARP scaling, I definitely need to look into more. Layer 2 topologies, I think I need to get a better understanding of as well. But layer 2 and 3 routing for self-redundancy protocol, I think even hardware to an extent, I'm probably good on. Routing, I'm definitely going to need a big refresher for BGP, but that, yeah, so BGP will be a big part of this series as well. Okay, in addition to that, we got a really good look into HTTP, so we'll be looking at that more closely again, but I feel pretty good with that. Going through the console, learning how those GET messages work, learning the 401 responses. I think another common one is like a 500 error, like the server is offline or is having some sort of issue. That'll be in the 500 range. So yeah, and then we're going to be looking at fundamental stuff. Maybe not as much time on that, but the biggest thing I'll be looking at throughout this series is BGP, layer 2 topologies, and ARP scaling. Yeah, that's the end of this first video. So I will see you in the next video of this new series to explore real-world networking that you might see in the wild and not just on a test. Thanks for watching.